Hi guys, welcome to today's lesson. So today we're going to be looking at some Euclidean geometry, right? I know this is one of those topics that really gives you quite a little bit of a challenge, but we're just gonna look at it, and then I know that because you are watching these shows and you are enjoying them, you're actually gonna learn something, and it's gonna be a bit easier for you to then do them going forward. So specifically under Euclidean geometry, we're going to look at some similarity, right? And we're going to look at some calculations that have to do with similarity. What does it mean when you say two things are similar? The word similar itself, when you look at it from an English perspective, one will think, no, they must just look alike and all of that, but that's not really the case. Mathematically, it means something very different, but we'll look at that as we go on. For now, let's just look at the map of this lesson and see what is it that we need to look at by the end of this lesson. So, I'm going to look at some proportionality, similarity, and equiangular. So, when two triangles or two shapes are proportional, we claim that they are similar. And if they are similar, it then means that they are equiangular, right? We then gonna also look at some some midpoint theorem, and some Pythagoras theorem as well. In terms of riders, the types of questions that you will get under similarity are in two categories. One is when you need to show that the triangles are similar, given that the sides are in proportion, or the other category will be to find the length of sides of similar triangles. And then these are just the two categories that we can then categorize the types of questions that we are going to get under similarity. Our leading question for this lesson will then be, how can you then use Euclidean geometry to solve practical problems? I give you a shape that has a circle, it has a triangle, it has a square. How can you then use Euclidean geometry to try and solve that particular question? That's our leading question. Now, the key words for this lesson as well will be proportion and ratio. So let me just give you a quick explanation of what a proportion means. Proportion means that, let's consider maybe I have square A, B, C, D, right? And also another square here, which is, just assume that it's a square, although it's not drawn to scale. E, F, G, H, right? Both of them are squares. I just didn't draw them to scale. Now, if the length of this square is 2 and the length of this square is 8, 8, 8, 8. So it means that for me to move from one side of the smaller square to the other side of the bigger square, it will then be me multiplying by 4. If I say these two shapes are in proportion, it means that even to move from one other side to the other side, it must be the same as moving from the other side, which is the third side, to the third side, from the fourth side to the fourth side. But if I move from the first and the second to the first and the second of the other, I multiply by a certain number. But from the third and the fourth side, I multiply, and the number is not the same that I'm multiplying by, then you're not talking about things being in proportion. So I hope you understand what I mean. And we then compare this using the concept of a ratio. Similar triangles, guys, one thing for sure that you need to know is when we talk about similar triangles, size is of very least importance here. It is really not something that you need to even concern yourself about. So these things will be different in size. One can be very big, one can be very small, it doesn't matter. As long as the three angles in those two shapes are equal to each other, right? The corresponding angles. So as you can see, the angle at that on my left-hand side will be the same angle as that on the left-hand side with those colors, and the red angle with the red angle, and the blue with the blue, right? And then I will show you this when it comes to some questions that we're also going to look at. Also, similar triangles are named in order of the corresponding sides, right? We name these in the order of the corresponding sides. So for example, the side AB must correspond with the side XY. So side AB will be that one, which must correspond to the side XY. And also the side BC must correspond to the side XZ, which will then be the XZ there and the BC, and then the last side will be AC, which must correspond with the side XZ. Now, I know that this is really something that you are used to, because when you talk about ratios, you will see that we'll be using the corresponding sides in terms of those ratios. And it's important for you to know them the way I've just tried to show you in terms of A, B, C, and X, Y, Z. Now, similar triangles, this is the ratio that I'm talking about now. The ratio of the three corresponding sides will always be the same. So, AB and XY, meaning across, right? So it will be this AB here and that XY. Remember I said they are corresponding. BC and YZ, remember we said they are also corresponding. And CA and ZX, they are also corresponding. Now guys, with these things that we've just spoken about so far, proportionality, right? Two triangles to be similar to each other. One, we said that the angles must be equiangular, right? The size of the sides and the shapes do not matter. What matters is if those sides are in proportion based on us using ratio, then we can claim that they are similar to each other. They don't necessarily need to be the same thing. No, as long as it's the same category of shapes, triangle and a triangle, because you can't compare a triangle and a square and then say you want to talk about similarity there. That will not make sense. So that's what you need to please understand with that. Now we have a theorem which is called the converse equiangular theorem, which states that if corresponding sides of two triangles are proportional, then the triangles are equiangular. What does that mean? It means that if the two triangles that we have corresponding sides, meaning the sides are in proportion, one, for you to move from one side to the other side, you're multiplying by the same factor throughout, then the angles in those two triangles will also be equal to each other using the correspondence in terms of the triangles when you label them. And consequently, we then say that those two triangles are similar to each other. Why? Because the corresponding sides are proportional, which makes the angles to be equal, and then we then claim that they are similar to each other. And normally our reason is sides of triangles in proportion. Now let's try and apply this just so that we can see exactly what we're talking about, right? If I compare the side AC, or BC rather, and the side AC, it must also give me the same ratio if I compare the longest side, which is 8, and that's XY for the smaller triangle, and the shortest side, which will be the 5 there, which is YZ for the other triangle. Now, the question is, determine if these two triangles are similar. How do you do that? By doing those comparisons that I just showed you now. If I find that my ratio of AB with BC is the same as my YZ all over YX, right? Then I can claim that these two triangles are similar to each other. If that is not the case, then I'm not doing the right thing there. So let me just try and see whether this will definitely work. So this will be 20 over 32, and it must be equals to the YZ over YX, right? So firstly, let's simplify this. The highest common factor of these two numbers will be 4, which will then give me 5 over 8, right? And then let's look at yz over yx. This is equals to 5 over 8. So you can see that these two are equal to each other. So our required to prove is actually proven, because remember I said if we want to prove that they are similar, then this ratio must be true. So you can already see that the ratio is true, that is here. So I know that I already started with making them to be equal before actually solving them, but this is not really the order of you working this out. So when I ask you to prove that the two triangles are similar to each other, you don't start by already saying that their ratios are equal. No. You find the ratio in one triangle, you find the ratio in one other triangle, and then if those two ratios are equal, then you can claim that they are similar, right? Hence, I said the one at the top there is actually my required to prove. That's what they want you to prove, that the ratios are the same. But you don't start immediately by making them the same, because then that's something else. You are now making it seem like you do know that they are similar to each other. So that's one of the examples that you can look at, please. Now, let's look at another, it's the same equation, right? I only used two ratios here. We need to also look at other ratios. So the other ratio will then be, if I look at AC, right? That's the middle side in terms of the length, and I want to compare it with the BC, right? This will be equals to AC is 24 over 32, right? And then the answer that I'm going to get here, which is the ratio, will then be if I divide both these by 4, because that's my highest common factor, it will be 6 over 8, right? And then we go to the smaller triangle. AC is the side that is between the smallest and the biggest side. So the side that is between those two, according to the smaller triangle, will be XZ over, and the one BC is the longest side, which is XY. So XY. And then you look at what is the ratio there. That is 6 over 8. Do you see? Already they are equal to each other. So you can see that if I use the last ratio as well, it will still be the very same thing. But for argument's sake, let's do it as well, so that I show you exactly what I mean. Now I've compared XZ and I've compared it with the XY there, right? Now I want to compare the YZ with the XZ, because I haven't compared that. And if I do that, it's the smallest side and the following one in terms of ascending order. So that will be YZ, which is over XZ, and this will be 5 over 6. This must be the same as, what is the smallest side on the bigger triangle? It will be the AB. So that must be the same as AB over, and then the following one is AC, right? Or CA. AC, which is equals to, so the AB side there is 20 over, my CA is 24. And then if you find what is the highest common factor between the two, it will be 4, which will end up being 5 over 6. Then you can see that it is also the same as that. So you can see that the ratios throughout are giving us the very same value as you are comparing them across board. And then that will make them to be similar to each other. Now also, here they want us to determine the length of XZ, right? Firstly, we need to show that these two triangles are similar to each other. They did not make the statement that they are similar. If they did, then you'd go straight to the ratio. But first, we need to show that they are similar or not. And what I will do is compare this 15 here, which is my PQ, with the QR there. And after comparing that, I must also compare the XY and the YZ there. If they are equal, then it means they are similar, right? So that is 15 over 30, which is the same as 1 over 2. So you can see that, right? And then I said also 9 over 18, which is also 1 over 2. So what? So what is the conclusion? They are similar to each other. Then I can just go to the ratio. Since they're similar, it means the ratio of x, z over my yx must be the same as, so remember it's the one at the bottom there, it must be PR. So PR over, I also chose the 15, which was the one PQ, right? So that is PQ. And then you can find XZ using that. So I don't know what this is. I will let it to be X, and this will be 9, and this is equals to 20 over, my PQ is 15. And this becomes 15x equals to, and then this will be 9 multiplied by 20. Then lastly, my x will be equals to 9 multiplied by 20 divided by 15. Then you can just press your calculator. It will then give you your length. All right. So guys, that's what you then need to know about this. You need to be told that they are similar. Then you can go straight to the ratio. If you are not told, quickly with 2 steps, show that they are similar and then use the ratio if they are similar. I hope that is a bit clear for now and you are still enjoying this. Just take a quick walk and drink some water so that there can be some flow of blood in your body, and then I'll be back just after the quick ad break. Hi guys, welcome back. So we are still busy with some Euclidean geometry, specifically similarity, right? Now, there's a concept that you've been using almost ever since you started doing your geometry, and this is the Theorem of Pythagoras. So now we're going to try and use some similarity to prove the Theorem of Pythagoras, just so that you can see exactly where does this come from. Because I know we've been saying to you the square of this is equals to the square of that plus the square of that, but what exactly is this? Where exactly does it come from? That's what we're going to try and do right now. So let me just take you through that, and then we can see if we can look at exactly where do we take this from. So here, this is still our mind map of what we've been looking at so far. Now, the Theorem of Pythagoras, you know that the condition is it must be in a right-angled triangle, right? The square of the hypotenuse side is normally equal to the sum of the squares of the other 2 sides. And your reason is normally just Pythagoras, right? And mathematically, you know that the hypotenuse side, we normally use it as r. So r squared is equals to x squared plus y squared. That's what the Theorem of Pythagoras says, right? When you talk about the sum of the squares of the other 2 sides. Now, to prove this, the first thing that you need to do, so because this is a formal proof, you start with a construction. And the construction will be to draw a line from the vertex where the 90 degrees is, so that this line intersects with the hypotenuse at 90 as well. So there must be a perpendicular relationship between the line that you are constructing. Now, this will look like this, right? So you draw from vertex C or to the line AB such that it is perpendicular to that line, right? And then the condition here will then be, we then need to try and prove that this triangle AEC, is similar to the bigger triangle, which is ABC. And also prove that the triangle ECB is similar to the bigger triangle ABC, right? So what am I trying to say? The first condition is to prove that AEC, right, is similar. So similar is normally the horizontal, the vertical lines. You remember that, the three vertical lines. Is similar to the triangle A, because E is a 90, it must go with CB like that, right? So I must prove these two, number one. And then number two, I must then prove that the triangle EC with the B, it must also be similar to the other. Might not really be the same, but the concept is what we're trying to look at. Triangle CAB, right? So it must really be that these two triangles are similar to each other. From this, we'll then look at what we can do. Remember, to prove similarity, we either use sides in proportion or we use equiangular, right? So I will then say in triangle AEC and triangle, so I'm just going to label them first so that we have a focus, ABC. I know that the angle A is common, so angle A is common, and I know that the angle AEC is equal to the angle ACB, which is equal to 90 degrees. Remember, that was the condition of you constructing the line. Automatically, because the two angles are equal, it makes the third angle to be equal because of the sum of angles of a triangle. So that makes the angle ACE to be equal to the angle B, right? I will just say it's angle B. And my reason for this will just be remaining angles of a triangle. Therefore, you can claim that the triangle AEC is similar to triangle. So A is A, right? It goes with the other angle at A, and then CB like this, right? And my reason here will be equiangular. Equiangular. Remember, you do write your reason, equiangular, because you've proven that the angles are equal. And then because of this, we then look at another triangle, right? Or another pair of triangles, which will be this one here, my BCE, and the bigger triangle again. So I will start by labeling it again. In triangle ECB, guys, I really, really hope you are following me here, because I can see that it's quite a lot of things that I'm writing here, but please do try to follow me as much as you can. If you can't, just write it down so that you can go over it again after we are done here. A, B, C. Now, I will then look at these two triangles. I can see my angle B is common, so I will say angle B is common. Already I know that. Angle B is common. And then there's a 90 degrees in both the triangles, right? So that will make it BEC, which is equals to ACB, and this is equal to 90 degrees. Then you know the third angle will be equal, and the third angle, according to the two triangles, it will then be ECB, which will then be equals to the angle A, and my reason will be remaining angles. And then you can claim that the two triangles are equiangular as well, right? So I'm going to write them down this side. The first pair that I proved to be equiangular was AEC and ACB. So triangle AEC, we said it was similar to triangle ACB. And then the second one that we proved was BEC, which was similar to BCA. Triangle BEC, which was similar to triangle BCA. Good. Then we're going to use this to then show that the two the square of the longer side is equals to the sum of the other squares. Now, guys, the theorem of Pythagoras is one very important tool to try and find an unknown side when we are given the other two sides, right? Or when we then start talking about the concept of circles, you will see that to find the radius and all of that, we use this concept. But it is a very important concept. So now what we're going to do, we're going to link one side, that is the hypotenuse side, on one triangle, and link it to the other side, which is the hypotenuse side on the other triangle, and see whether we can then find some similarities there in terms of the ratio. So, in the first scenario, which is number one, so I will call it number one, I know that if I have AC over, so AC, it must go with, in the very same triangle that I have, because I'm trying to look at the side AE, right? So I will make it move with the AE there. So that will be AE. Then it must be equals to, because I took the last ones there, it must go with the AC there, right? So AB will be the hypotenuse side, so that's AB over AC. If I simplify this, it will then give me AC squared is equals to AE multiplied by AB. I leave it there. This becomes like my equation number one. And then I go to the second scenario that we spoke about of similar triangles. Now I will say if I want the hypotenuse side of BEC, the hypotenuse side of BEC will be BC. So BC must go with BA. Because I want to link it with the longer side of the bigger triangle, which is AB. I will link it with EB, and this will link with BC. So it will therefore be BC over BE is equal to BA over BC. And then also I cross multiply here. It becomes BC squared is equals to BE multiplied by BA. Now you can already see that if I was to add these two, then there will be some similarities that I'm going to find there, right? So let me just show you what I mean. I'm going to say, if I can say AC squared plus BC squared, let me show you on the diagram. The AC squared will be the B there, the small letter B, plus the BC squared will be the small letter A. It must be equal to this one here, which is the small letter C, according to the theorem of Pythagoras. So that's what I'm trying to find there. So this will be equals to, that is AE multiplied by AB plus BE multiplied by BA. And then you know, guys, there's AB there. I can take it out as a common factor. So that's AB into AE multiplied, BE. If I add my AE and BE, it will give me the whole of AB. So now I land with AC squared plus BC squared is equals to AB into AE, remember, plus EB. And I said to you, what is inside the bracket, if I add it, it gives me AB. So this becomes AB multiplied by AB, and it will therefore give me AB squared. So this will be AC squared plus BC squared, AC squared plus BC squared. And then if we use the small letters, the small letter for AC is B, the small letter for CB is A. So this is B squared plus, this is A squared, which will then be equals to C squared. And that's how you then prove your theorem of Pythagoras. So I do know that all of this just looks like it's a lot of work that you need to do, but it's mainly just for you to know where the theorem of Pythagoras comes from. Guys, I can already see your faces there. You are thinking, yo, what is this man trying to say? But honestly, if you wrote it down and you go back and re-look at it, I promise you, you are going to get it. And then just try to see what is the concept here. The concept is proving the smaller triangle with the bigger triangle, that they are similar. Another small triangle with the bigger triangle, that they are similar. And then link those so that you can try and prove the theorem of Pythagoras. I promise you, it's really going to work. But because I've really been doing a lot of talking here, let me just give you a quick ad break and I'll be back with some more. So please stay tuned. Hi guys, welcome back. So guys, we are on our last segment of today's lesson. So we've been looking at a whole lot of things. I know that the second segment before we went to the ad break, I actually said a lot. I actually listened to myself as well as I'm saying these things, and I thought, yeah, hey, I'm saying a lot of things here. I'm hoping that you guys are following me through. But remember, I said you must please write it down so that even if you didn't hear a few things, you can always go back to what you wrote down and try to link what I said with what you are seeing there, and then it will be okay for you. Also, remember to consult your textbooks, consult the internet, like consult everything that has some knowledge in mathematics that can help you understand these concepts better. For now, let's do some riders. Riders is, remember I said it's when you're doing some questions that have to do with Euclidean geometry. The first one will be mainly to prove similarity, and then the other one will be to then use similarity to just do some nice things, some very beautiful things. But for now, let me show you what the first question is all about. So, the first question says here, chord AQ of circle with center O cuts BC at right angles at point P, right? Now I know I've been doing triangles without the circle, but what I'm trying to show you here is we can link these triangles with some circles, right? And although we are not yet looking at the theorems that have to do with the circles and all, but you have done that previously, we're actually just looking at the similarity, the proportionality, the ratio, but within a circle, because those two things can be linked to one another. Remember that a circle can really take anything. It can take a quadrilateral, it can take a triangle, it can take any regular polygon or irregular polygon. So that's why I'm just trying to now use a question that has a circle for you just to see that they can be linked. Right? So the first question says that we must show. Hey, I love this question. Why do I love this question? It's because you guys will then be creative and try to work it out, and then it doesn't work out, and then you end up saying, no, they are not similar to each other. But I said to you, just show them. When I say show, it is because they are indeed similar. So you just need to show me the order of how did I conclude that they are similar. I'm not saying prove whether or not. I am saying prove that they are similar because I know that they are similar. So I will never give you a question that says show and then your answer will then be the opposing solution to what I said you must show. And then the last question has to do with solving some sides there, but for now let's look at trying to show what I want you to show, right? Now it's triangle ABP, so I'm going to have to highlight it on my diagram there so you can see exactly what we are talking about. And this is how you then solve this, guys, effectively. So it's ABP, that's the one there, and the other one will be CBA, so that's the bigger triangle, right? So I will make it like a wobble of some sort so that there's some difference there. I make it a wobble like this. Good. So those are the triangles I want you to work with and try and show me that they are equal. So let's go and on the triangle. I know that since this is a 90 degrees on this side It means even on this side it's a 90 degrees because these angles are on a straight line, right? And also the two triangles have the angle B being common there. Already you can see that. So the very first thing that I'm going to do, I'm then going to say in triangle ABP and triangle CBA, the angle B is common. Both triangles have angle B. That's what angle B is common mean. And also the angle APB is equals to 90 degrees, and this will be because it is given. And then remember, because this is a semicircle, and I know that an angle that is subtended by a diameter in a circle, it must be 90 degrees. So that will make the angle A there to be 90 degrees as well. So I will then say angle A is equals to 90 degrees. And what will be my reason for this? It will be angle in semicircle. Semicircle. From there, I can then claim that the last angle in the two triangles is equal. Why? Because of remaining angles, right? So the last triangle, the last angle in triangle ABP is angle B, right? Not angle B, but angle A, right? So it will be angle BAP. And this will be equals to the last angle in the other triangle will be C, angle C. And the reason for this will be remaining angles. And now some people, they don't use the word remaining angles. They use the sum of angles in a triangle. It's really up to you. They mean one and the same thing. For you to get a remaining angle, it must be because of the sum is the same in the two triangles. And therefore, I can then conclude that triangle ABP is similar to triangle CBA. Now let me show you something very interesting here, guys, that I need you to use when you are trying to prove similarity. If I've given you the triangle ABP and CBA like that, it means the angle at A on this triangle must be equal to the angle at C on that triangle. The angle at B must be equal to the angle at B. And then the angle at P must be equal to the angle at A. So you see, that's how you just gauge yourself to try and solve this if you don't even know where to start, right? Let's try and see whether that's what I did. The angle at B is X and X on the two triangles. So is it equal? Yes, because it is common. Let's look at the other one. The angle at P, I said, must be equal to the angle at A. Let's see. Angle at P is 90 in one triangle. The angle at A is 90 in the other triangle. Voila, it's also equal. Let's look at the last one. The angle at A in the triangle ABP must be equal to the angle C in the bigger triangle. Is it equal? Yes, because of remaining. So you see, that's how you can just gauge yourself if you don't know where to start. Now, lastly, let me just give you the reason for the claim that we made. This will then be angle, angle, angle. And some people just write it as angle, 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 or they say equiangular, but they mean one and the same thing. All right, so the second question then says, if AB is equals to root of 6 units, and PO is 2 units. So the first thing to do is to go to the diagram and write down the values that you are given, right? So they said this is a 6, square root of 6 that is, and this is 2 units. Then what do they want us to do? We need to find the radius, right? But what that actually means, they just want you to find the length of BP. If you know what the length of BP, then I can just add it to the 2, it will give me the radius, right? So I will immediately then say, let's let my BP to equal to X, right? just so that I know that I'm going to be using X and not BP and all of that, although it will still give you the same answer if you do use the BP. Now from that, it will mean that my OB, which is the radius of the circle, will then be 2 plus X. And if that is the case, then my BC, which is the diameter of this, will then be 4 plus 2x. Remember, the diameter is twice the radius of the circle, right? So I'm going to go back to the ratios that we wrote. It's ABP and CBA. So I'm just going to write them here. It's ABP and my CBA. So it means that the ratio AB, if I do need AB, yes, I am given AB. I must link it with something else that I know, and that something will be the BP here, right? And then that means it will then be BC, which will then go with the BA. Do I know what BC is? Yes, I said it was 4 plus 2x. Do I know what BA is? Yes, it is the square root of 6. So this means that this will therefore be AB over BP is equal to CB, or BC rather, over AB as well. And this will be square root of 6 over the value of BP there is, remember we said let's let it to be X, and this is equals to my BC will be 4 plus 2x divided by the square root of 6. And then from there, if I simplify this, I will get 6 there is equals to 4x plus 2x squared. And if you divide everything by 2 and then take the 6 to the other side, it gives me 0 is equals to, this will be 3, which must be a negative, so I must quickly erase that. So it will be a negative 3, not just a positive 3. So this will be x squared plus 2x minus 3. Factorize this, it gives me my answers. So this will therefore be x plus 3 into x minus 1. Therefore, automatically you can see that from what I've written here, the x will be minus 3 or it will be positive 1. So I will just say, therefore, x is equals to 1 because it cannot be equal to negative 3. Then you conclude the radius, because that's what they wanted us to find, will then be equals to 3 units. And then I'll be done with this. All right, so remember, as soon as you are given some extra information on the statement, you go straight to your diagram and then write down whatever information you are given and then solve it from there. But the main thing that we are solving using here is the similarity that we've proven before. So the summary, you must recall the midpoint theorem, which you did when you started doing your core maths, which is normally in grade 10, and the converse thereof, and then the conditions for similarity. How do two things become similar to each other? And then similarity theorems, remember the proportionality, equiangular, and what we've looked at so far. And then the last thing is the Theorem of Pythagoras. I promise you, if you do recall that, it will be very beneficial for you to solve some Euclidean geometry. Guys, I know that geometry is a bit of a to your head whenever you are trying to think about it. It's like that little bit thing that actually pokes you whenever you're thinking about it. But please, try it, guys. You can only try, and I promise you, if you try, you will definitely get it right. Write down some things. If you don't understand, go back to them, relook at them, consult the Google, consult your textbooks, consult your teachers, just consult everything that has knowledge of mathematics. I promise you, you're gonna get it right. From me, the maths doctor, to you, remember, mathematics is food for the soul. Until I see you next time.